And we'll just look at some examples. So we'll start off with this one here. So we've got a tank, it's got 30 litres of solution of some particular chemical in the tank. We've been told that the concentration is going to be reduced, so pouring water into it, so diluting it down. And that's coming in at a rate of 1 litre per minute. But also, because we don't want the tank to overflow, so it's flowing out at 2 litres per minute. So I guess eventually that tank will be empty, won't it, if we're only pouring 1 in and 2 out. So at any point in time, it contains X litres of the chemical. We have to show that the rate of change of that X is minus 2X on 30 minus T. It's all right, the information that we've got there. We know every minute the volume of the tank is reducing by 1 litre per minute. Yes, because 1 litre is going in, 2 litres are going out. So overall, 1 litre. So we know the volume at any point in time would be the initial volume, 30, minus T litres, because every 1 litre every minute. Now, at any particular time, the fraction of the solution that we have, we know we're going to have X litres. So X out of the 30 minus 2 litres, that'll be the fraction of the chemical in our solution. But we also know it's escaping at 2 litres per minute. So therefore, the rate of flow must be twice that. And it'll be negative because we know the volume is decreasing. So dx of t minus 2x on 30 minus t. So find the fraction of the original chemical still in the tank after 20 minutes. So that original volume, we don't know what it is, so let's just call it V for volume. And there's our derivative we just found, dx to t. First thing I'm doing is I'm coming up with an equation that's going to link x and t. But it would have been quicker if I just put 20 there straight away and got the answer. Anyway, we'll get there. So let's integrate. So I have log of x equals log of 30 minus t. We're trying to find x, aren't we? So it's x the subject. So there's our formula, but now I'll substitute when t equals 20. So that's what I was saying, it would have been quicker just to have 20 there, because then I could just substitute it in the integration itself. But anyway, whichever way I do it, I get v over 9. So the original one we said was v, so we've got 1/9 of the original volume left. So population of foxes on an island, y1 minus y, where y is a fraction of the island's carrying capacity. Part A, here's a different way of doing the same question. So use the substitution and you end up coming up with a simpler derivative. So we're going to use the substitution, y equals 1 on 1 minus w. Our equation will simply become dw dt is minus w. And in fact, that's just our basic growth and decay. So that will make it a much simpler problem, I guess. So y is 1 on 1 minus w. We want to show the w. So I'm going to differentiate both sides with respect to t. So the left-hand side, I just get dy to t. Right-hand side, doing it implicitly, reciprocal rule minus the derivative on the function squared. So I get 1 on 1 minus w squared. Divide the t, all the stuff we've found. So substituting it all in, multiply both sides by 1 minus w squared. And yeah, we got cancelling happening there. We end up with negative w. So we've got our equation that we want. All right, next part. Find the solution of our logistic equation. It's got to satisfy the initial conditions. When t equals 0, y equals a quarter. Where did I get that from? T equals 0, population of the foxes is 1/4 of the island's carrying capacity. Right. Okay, so a quarter is 1 on 1 minus w. Because now I've changed it to w, I've got to find the initial condition for w. It's negative 3. Okay. So we have this equation to solve, but we know the solution to that because that's our basic growth and decay one. Remember, that's just AE to the minus KT. So I'll end up with the initial minus 3, E to the power of minus T. Voila! There's our answer, because remember we said y is equal to 1 on 1 minus w. So now I just substitute that in. There it is. So how long will it take for the fox population to reach 3/4. So now we want to know, well, when is that 3/4? We just got to find t. And there we go. Eventually, t is the log of 9, which is 2.19722, 2.2 years. We have a rumour. We love our rumours. A rumour is spreading amongst 1,000 students in the school, and it's at a rate proportional to those that have heard it, but also those who have not heard it. So x have heard it, so therefore 1,000 minus x have not heard it. As time progresses, though, people care less about the rumour, so our proportion rate is not constant. So that's why you'll notice on the right-hand side, we've got it divided by t plus 1. So time has a factor of our rate of spread of the rumour. Initially, there's always one student starts spreading the rumour. And after 1 hour, 50 students have already heard the rumour. So how many have heard the rumour after 3 hours? Here's our derivative, but this is separable, isn't it? Yes. So we end up with dx on x, 1,000 minus x, is equal to k outside the integral of t, 1 plus t, matching up our conditions. Initially, only one person knows the rumour, that being the rumour mongerer. And then, after 1 hour, we know there's 50. So this will allow me to find the constant. We should be able to find the constant. Now, of course, this one here we can do via partial fractions. We have 1 on x plus 1 on 1,000 minus x. But of course, that would give me an answer of 1,000 for the numerator. So I need to divide it by 1,000 out the front to balance it out. And the right-hand side, oh, that's just simply the log of 1 plus t. So let's keep going with that. Left-hand side now becomes the log of x on 1,000 minus x. And I've multiplied both sides by 1,000, so it's gone to the right-hand side, is 1,000k log 2. All right, manipulating all that, we eventually get this wonderful statement. K is the log of 999 on 19 divided by 1,000 log 2. I think I'd just be storing that number in my calculator. I'm not going to play around with that. In fact, I'm going to leave it as k in the next line because I'm not going to write that down every single time. We'll just leave it as k. So now we want to find out when t is 3, what is x? Okay, so again, let's just go through our integration. So the log of 999, see, subbing 3 into this and then subbing 0, it's just going to be some constant number. The left-hand side, when I sub in x, then sub in 1, we'll end up with the log of 999x on 1,000 minus x. All right, time to work out c. C would be 1,000 times k, so now I've got to use the k that I had here, times, subbing into this, we get the log of 4. Tidying all that up, we get 2 log 999 over 19. All right. Exponentialise both sides. I'm leaving it as c. I'm not writing all of that down. All right. So 999x over 1,000 minus x is e to the power of c. So 999x is e to the power of c, 1,000 minus x. Again, I've just kept that number in my calculator. Punch the buttons. X is 734.558. Almost the whole school. It was 1,000, it only took 3 hours. See what rumours can do? So 734 students have heard the rumour.